In this lesson, we will continue on with complex numbers. At this stage, we have defined what a complex number is. So now we're going to go a bit further and see what we can do with them. We'll show you how to get the modulus of a complex number, which is basically the distance from zero, and the conjugate, which is useful also. And we're also going to show you how to add, subtract, multiply, and divide complex numbers. So let's start by reminding ourselves what the definition of a complex number is. So we'll call it Z, just to give it a name. So Z equals A plus IB. And A is what's called the real part of the complex number, B is the imaginary part, and I squared is the root, I squared is -1. So this number I is an imaginary number. We cannot work it out because we don't know how to solve this equation, I squared is -1, or we don't know how to get the root of -1. Okay, so the next thing is we need to just remind ourselves also what that looks like on a diagram. An Argand diagram is what it's called. So we have a real axis and an imaginary axis. So when you have a number like A plus IB, that means you go A units across. So there's A, and you go B units up on the imaginary axis. So that's BI. And that's the number there, that's Z. So Z equals A across. It's very like the XY coordinate system, but it has a different meaning because we have a real axis with real numbers and an imaginary axis with imaginary numbers. So there is Z equals A plus IB. Now, the first thing we're going to talk about is modulus. So this word modulus, what does it mean? So if that, we'll say that number Z there is equal to, it's written as this, 2 lines with a Z, that means modulus. And in plain English, it means the distance of Z from 0, or the origin. On the calculator, there's actually a button for it. It's ABS, the absolute value it's called as well, of whatever the number is. So on the calculator. Okay, I'll just tidy up the letters there. The L and C look similar. So it's on the calculator, it's the absolute value of Z. Now, an example, or just in general first, I suppose, if we just look at the diagram we have, and we look here, from here to here, for example, that is the modulus, that distance there, whatever that distance is. We actually call it R very often because you can imagine it as being the radius of a circle, and the circle would continue on. You can imagine the circle centered at 0 that goes on in both directions like that. So that's why it's called R sometimes. And so as we said, R is now the modulus of Z. That's what it's called. How do we work it out? Well, we'd work it out by looking at basically Pythagoras. You can see here quite clearly that this is a right angle triangle. So we put our right angle in here. And now it should be clear that this is A units across. This is B units up, whatever B is. We ignore the I because it's just the distance that we're interested in. So that's a distance of B units. And now we can see quite clearly that it's a right angle triangle with A squared, because of Pythagoras, A squared plus B squared is R squared. So A squared plus B squared is R squared. So if A squared plus B squared is R squared, well then R is the square root of that because of Pythagoras. And there's our definition of what's called the modulus of a complex number. It's the distance from 0, and we get it by Pythagoras. And the great thing about knowing this definition is from now on we don't need to draw the diagram anymore. We can just work it out using that formula. So some examples. So if you had, for example, Z is equal to 3 plus 4i, well, the modulus of Z is the root of 3 squared plus 4 squared, which is, if you work it out, that's just simply 5. If you had Z equals -2 plus 7i, for example, the modulus of Z is equal to the root of, you just include the minus, so it's -2 to be squared plus the 7 to be squared, which is 7 squared is 49, 2 squared is 4, so it's, or minus 2 squared is still 4, so it's root of 53, for example. So it's as simple as that. If you keep in your mind that it's the distance of the number, the modulus means distance from 0. That's all it means. And you can work it out always using Pythagoras' theorem. Of course, there are even simpler ones. I mean, if z is equal to 3 plus 0i, that's 3 along the x-axis, or the real axis. Well, then the distance is 3, because there are no units. So the modulus is simply 3. It's even easier in that case, because it's 3 units along the x-axis, or the real axis. And one more maybe, if you had z is equal to just 4i along the y-axis, well, that's 0 plus 4i really. So the modulus of z is simply 4 units. It's 4 units away from 0. You ignore the I, which is very important. You ignore the I in that particular situation. So back to the start, the 4 things we were going to do today: modulus, conjugate, add, subtract, multiply, divide, there are 6 things there altogether. So we have done modulus now, so let's move on to conjugate. And conjugate is even easier. It's an easier concept again. Conjugate. It's called z hat, like that. That's the notation we use, z hat. So this is what's called the conjugate of a complex number. So the best way to explain it is some examples, really, some simple examples. So if you had, for example, z is equal to 3 plus 4i, 3 plus 4i, well, z hat, or conjugate of z, is 3 minus 4i. If you had z is equal to 2 minus 6i, z hat is equal to 2 plus 6i. So you see, you catch on to this after a while without me even explaining what it is. Just by looking at examples, you can see what's going on. It's just the sign in front of the I part changes. So whatever the I part is, changes sign. And you could take something like z equals minus 6 minus 4i. As I said, it's only the sign in the I part changes, not the other sign. So z modulus is minus 6 plus 4i. What else can we talk about? So something even simpler, maybe z equals minus 6 itself. What's the conjugate of a number on its own, like minus 6? Well, minus 6 is really minus 6 plus 0i. So the conjugate of that would be minus 6 plus 0i, minus 0i, which is the same thing. It's still minus 6, basically. And that's conjugate done. So we have 4 more things left to do: add, subtract, multiply, and divide. So we'll now do addition. And addition is quite easy. Again, the best way is with an example. So if you had z1, we'll call it z1, just to christen it, give it a name, 3 plus 4i. And if you had z2 is equal to 4 plus 7i, or something like that, well, then what is z1 plus z2? z1 plus z2 is equal to, all you do is 3 plus 4i, and you're going to add 4 plus 7i. And just add like terms. It's just like algebra, really. So you add the 3 and the 4 and the 4 here. So 3 and 4 is 7. And 4 and 7 is 11. So you add the I parts as well. 4i and 7i is 11i. And that's addition done. Subtraction is just the same. So subtraction, another example. So you could guess this one as well. Take the same 2 numbers. So if z1 is equal to 3 plus 4i and z2 is equal to 4 plus 7i, well, then if you get z1 minus z2, well, that's equal to 3 plus 4i, take away 4 plus 7i. And again, similar terms, like terms together. So 3 minus 4 is minus 1. So that's minus 1. That's the real parts taken care of. Now do the imaginary part separate. So 4i and 7i, that's a minus, of course, minus 7i, because there's a minus outside the bracket. So it's 4i minus 7i is minus 3i. And that's subtraction done. Now we're left multiplication and division. So multiplication is next. Again, an example. So take the same example again, where z1 is 3 plus 4i, z2 is something else, 6 plus 3i, or plus 5i, make them different. What is z1 multiplied by z2 this time? Well, it's 3 plus 4i multiplied by 6 plus 5i. And again, you just multiply them out just like brackets in algebra. Imagine the I was an X, for example, what would you do? And so you work just like that. So everything in the first bracket is multiplied by everything in the second bracket. So 3 by 6, so it's 3 into 6 plus 5i plus 4i into 6 plus 5i. 3 6s is 18, 3 5s is 15, and plus 4 by 6 is 24i, plus 5 by 4 is 20, and I by I is I squared. Now, again, at this stage, we keep like terms together, so that should be 18 plus 15i actually. 18 plus 15i. So now keep the i's together. And there's something else going on here as well. I squared, if you go back to our definition of complex numbers, where this all started was we didn't know the value, the result of I squared equals minus 1. We can't evaluate that equation, I squared is minus 1. But I squared itself is minus 1. It's just the I we can't evaluate. So whenever you see minus 1, this is the big difference from x's or algebra, I suppose. If that was an x, you just leave it as x squared. But because we know I squared is minus 1, we replace that with minus 1. And now we have 18 plus 15 and 24 is 39i, plus 20 times I squared is minus 1. And now you have 18 plus 39i minus 20. And now keep the real parts together, keep like terms together. So 18 minus 20 is minus 2. And that's it. That's Z1 multiplied by Z2. That's how you do it. So you treat it just like any algebra, like x's, until you get to I squared. That's the only difference. I squared becomes minus 1. And then at the end, you keep the real parts together and imaginary parts together, and you end up with another complex number with a real part and an imaginary part. So you could go off again then if you like and plot that on an R-gram diagram. And that's multiplication done. So we're on to the last one, which is division. Now again, an example. So the example is this. Take two numbers like Z1 equals 3 plus 4i, Z2 equals 5 plus 12i. And we're going to divide them this time. Z1 divided by Z2 is equal to 3 plus 4i divided by 5 plus 12i. Now we have a new problem here that we haven't had before. We're dividing by a complex number, and we don't know what I is. This is the whole problem. So if we don't know what I is, we don't really know what it even means to divide by a complex number. I mean, at least if you're dividing something by 5, by a real number, you know it's like dividing something between 5 people, for example. But 5 plus 12i, to divide by that, we don't even know what that means. So our first problem is actually not to divide, but to get rid of the I below the line completely. Use some kind of a trick to get rid of the I so that it actually means something again before we actually divide. That's the technique here. And what you do then is you rewrite it, 3 plus 4i over 5 plus 12i, and you multiply it by 1. This might seem like a strange step, but the thing is, anything multiplied by 1 is itself. So we still haven't changed the fraction, so we're still not doing anything illegal as such. And now the 1, we look at the 1 more closely. 1 is anything divided by itself is 1. So we can actually be creative here and say, get the conjugate of what's below the line, and we'll explain why we're doing that in a minute. In the next step, it'll become obvious. But the conjugate, which we just talked about earlier, the conjugate of 5 plus 12i is 5 minus 12i. And to compensate above the line, we do the same thing, multiply by 5 minus 12i. And the beauty of this is it's still 1 overall. It's still 1 because anything over itself is 1, so it hasn't changed. But by introducing this below the line, we have now got a way of getting rid of I completely. Because when these multiply out, the i's always cancel. If you multiply a number by its conjugate, the i's will always cancel. And that's the key step here. And that gets rid of the problem we have, which is the I below the line. So watch how this happens. We'll multiply top by top first and then bottom by bottom. So it's 3 plus 4i multiplied by 5 minus 12i over 5 plus 12i multiplied by 5 minus 12i. And let's just multiply out the brackets. So it's 3 by 5 is 15. 3 by minus 12 is minus 36i. 5 by 4 is 20i. And 4 plus 4 by minus 12 is minus 48i squared. Now below the line, there is a shortcut. You might recognize this is actually now x plus y by x minus y. So that's a shortcut. The answer is x squared minus y squared, difference of two squares. But even if you don't spot that, you can just multiply them out anyway and it'll still work. So 5 by 5 is 5 squared is 25. 5 by minus 12 is minus 60i. 12 by 5 is plus 60i. And finally, plus by minus is minus 12 12s is 144. And the I is squared. And here's something we've come across before. I squared is just minus 1. And these i's cancel, plus and minus. So the i's have disappeared below the line. And this will always happen if you do this right, if you multiply by the conjugate below the line. And now we can move on from there. So it's equal to 15. 20i minus 36i, so keep your i's together, those to go together. So 20i minus 36 is minus 16i, minus 48 by I squared, which is minus 1. Below the line we have 25 minus 144 by minus 1 again, which is equal to 15 plus, now that's plus 48 and 15, so now keep your real parts together. That's now real and that's now real. That's plus 48 and plus 15, 48, 58, 63. So it's 63 minus 16i over. Below the line we have plus 144 and 25 is 169. And there's one last step then, let's split them up. They're both divided by 169, so we can actually go 63 over 169 minus 16i over 169. That last step is necessary because we have to give the answer. This is the answer, by the way. We have to give the answer back in complex number format, which is a real part separate to an imaginary part, which we didn't have up there. So that's why there's one last step required. And I find people often forget this last step. Also, the other advantage of this last step is you could plot this now technically on an R-GAN diagram, because there's a real part and an imaginary part, whereas you couldn't plot this one up here as it's written at the moment. So that's it. We have, in this lesson, we have covered modulus of a complex number, which is distance from 0. We've covered the conjugate, which means changing the sign of the imaginary part. And we have covered addition, subtraction, multiplication, and division. And that's the end of the lesson.